All right, welcome back. So in the last lecture, we derived or discussed what it means for a function f of z to be analytic, which are very special functions in the complex plane that you can do calculus on, where you can take derivatives and do integrals, and where the derivative specifically is defined regardless of what approach you take to take that infinitesimal delta z goes to 0. So the derivative is the limit of delta f over delta z as delta z goes to 0. But because my variable z has a real and an imaginary part, I could take the limit as delta x goes to 0 on the real axis, or as delta y goes to 0 on the imaginary axis. And those two notions of the derivative have to be equal to each other for that derivative to be well defined, for df dz to be a function of z and not be kind of beholden or dependent on what approach vector or kind of approach direction I took to take that derivative. And so we actually computed, what is the derivative if I freeze delta y equals 0 and take the limit as delta x goes to 0, or if I freeze delta x equals 0 and I take the limit in the imaginary axis as delta y goes to 0. And those are two different expressions in terms of a complex function. Let's say f of z equals u of xy plus I v of xy. Remember, z equals x plus iy. And so my complex function has a real and an imaginary part, a real function u and an imaginary function v. And those functions, if I take the derivative df dz kind of on the real axis approach, then I get partial u partial x plus I partial v partial x. And if I take the derivative in the direction of delta y going to 0, I get that this derivative is partial v partial y minus I partial u partial y. And so for that derivative to be independent of the path I take that delta z goes to 0, these have to be equal, which means the real part have to be equal and the imaginary part have to be equal. And these are equalities in terms of the partial derivatives of the real and imaginary part of f with respect to the real and imaginary part of z. And if this is satisfied, then my function is analytic. These are called the Cauchy-Riemann conditions. Super duper duper important, okay? And so what we're going to say is, so that's just a recap of last time, that my function f of z, which has a real part and an imaginary part, this function will be analytic if it is single valued, if it's not multi-valued like z to the 1/2 or log of z, if it's single valued, and if these Cauchy-Riemann conditions hold for the real and the imaginary part. If these hold, then this derivative df dz is independent of the direction that I take delta z equal to 0. Good, very cool stuff. And examples of functions that are analytic that we see all the time are things like z squared, z cubed, z to the 4th, any monomial or polynomial in z, any function that has a convergent Taylor series like e to the z, cosine of z, sine of z, and even some exotic functions like log of z or z to the 1/2 or z to the 1/3, if I take them on their principal branch and I exclude the origin, which is kind of a very important singular point that is not analytic. And that I'll talk about later in the next few lectures. But things like z squared, z cubed, z to the 4th, e to the z, cosine z, sine z, those functions are analytic everywhere. They're called entire functions because they're entirely analytic everywhere in the complex plane. And they have very, very important properties that the real part and the imaginary part of those functions are solutions of Laplace's equations, the Laplace partial differential equation that comes up all the time in the heat equation, in electrostatics, in fluid mechanics. So that's what I'm going to show today. So if f of z is analytic, not catalytic, analytic, and both u and v are twice differentiable, and u comma v both twice differentiable. This is kind of like, sometimes mathematicians get almost a little bit lawyerly, where you have to be really, really careful about the specific conditions that hold. Like, of course, I'm going to be taking another derivative of these expressions, so I need them to be twice differentiable. So I'm going to write that into my little legal contract that we're all going to sign. If f of z is analytic and u and v both twice differentiable, then essentially what I'm going to do is I'm going to take this Cauchy-Riemann condition, and I am going to take its derivative with respect to x, and I'm going to take its derivative with respect to y, and we're going to see what happens. So, I'm going to take kind of Cauchy-Riemann 1. I think this is Cauchy-Riemann 1. Let's call this CR1. And just to be fun with colors, we're going to call this CR2. Okay. And the Cauchy-Riemann first condition is going to be, I'm going to take partial u partial x equals partial v partial y. And what I'm going to do is I'm going to take its partial with respect to x. I'm going to take partial of both sides with respect to x. And I'm going to get that partial squared u partial x squared equals partial squared v partial x partial y. Okay, that's what happens if I take the partial of both sides with respect to x. This is definitely true. And now I'm going to look at Cauchy-Riemann 2. What we're going to do is we're going to compute some derivatives, and then we're going to, make some things equal to each other, and we're going to show that the u function is a solution of Laplace's equation, and we're going to show that the v function is also a solution of Laplace's equation. So now Cauchy-Riemann 2, I'm going to take Cauchy-Riemann 2, which is, maybe I'll just mix this up. So this is, partial u partial y equals minus partial v partial x. And I'm guessing I'm going to take the partial of this with respect to y. That just feels right. Sometimes you got to trust your gut or try something and maybe it doesn't work. And this is going to equal, if I take the partial of this with respect to y, I get partial squared u partial y squared equals minus partial squared v partial x partial y. Partial, I take the partial of this with respect to y, it's partial squared v partial x partial y. Okay, so now what I have is that, partial u squared with respect to x and partial u squared with respect to y equal and opposite things. Okay, and so what this means, this is actually super simple. This means, maybe I'll go yellow again here. Because partial squared v partial x partial y appears on both the right-hand sides, this equals minus this. This equals minus the same thing. So partial squared u partial x squared equals minus partial squared u partial y squared. And if I add this to both sides, I get partial squared u partial x squared plus partial squared u partial y squared equals 0. This is Laplace's equation, del squared u equals 0. Equals 0 factorial also. So this is super duper important. If I have a function f which is analytic, meaning its derivative is defined and finite, and it doesn't matter what direction delta z goes to 0, if these Cauchy-Riemann conditions are satisfied, which is essentially synonymous with being analytic, then you can kind of manipulate these Cauchy-Riemann conditions and take some partials and set some things equal, and you find that the real valued function u, the real part of f, is a solution of Laplace's equation. This is called a harmonic function. Okay, so then u is a harmonic function. That's kind of what we mean when it's the solution of Laplace's equation. The solutions of Laplace's equations are called harmonic functions. The real part u is a harmonic function. It's a solution of Laplace's equation. Good. Just for practice, I'm going to show you how you would also derive the same thing for the imaginary part, for the v part. I'm guessing, again, this is just intuition, I'm going to take these exact same conditions, and instead of taking partial x of the first one and partial y of the second one, I'm going to flip those, and I'll get some other expression I can turn into a solution of Laplace's equation. So let's do that real quick, just for the sake of completeness. Same thing, Cauchy-Riemann 1 is partial, maybe I'll stick with some colors here. It is, we have partial u partial x equals partial v partial y. Again, I think now I'm going to take partial y of this, partial y, and I get, partial squared u partial x partial y. Sorry, it's so squeaky. I know it drives some of you crazy. Equals, now this is partial squared v partial y squared. That's good. That's what I want. Right, this is, now I want an expression that's in terms of the second partial derivatives of v, the imaginary part. So I got that here. And Cauchy-Riemann 2, I'll make this in pink. So Cauchy-Riemann 2 is going to be partial u partial y equals minus partial v partial x. And similarly, instead of taking the y derivative, now I'm going to take partial x. And I'm going to get, partial squared u partial x partial y equals minus partial squared v partial x squared. And actually, I think this one's even easier because now, the left-hand sides are equal to each other, so I don't even have to do any, mental carry the -1. This blue expression equals this pink expression. So I have, partial squared v partial x squared minus equals partial squared v partial y squared. And so if I add this partial squared x to both sides, I get, partial squared v partial x squared, the partial derivative, the second partial derivative of v with respect to x, plus the second partial derivative of v with respect to y equals 0. Again, v is a solution of Laplace's equation. So partial squared v equals 0 as well. Let's give it 2 exclamation marks as well. So v is also a harmonic function, meaning it's a solution of Laplace's equation. It is a harmonic function. Very, very interesting, okay? So this is pretty cool, right? Partial differential equations are everywhere. They are absolutely ubiquitous. Laplace's equation is particularly important. This equation comes up in every branch of physics. When you're solving the steady state heat distribution, use Laplace's equation. When you are solving for the electrostatic potential, or for the gravitational potential, or for a potential flow, for an incompressible irrotational flow, you're going to be solving Laplace's equation. And the neat thing is that solutions of Laplace's equation happen to be the real and imaginary part of these magic special analytic functions. So if I take something like if I take f of z equals z squared, which we know is analytic. We've shown this as analytic. And this equals, x plus iy, quantity squared. That equals x squared minus y squared plus I times 2xy. I claim that this, this real part u, this function u, and this function v are both solutions of Laplace's equation. You can verify it. You can actually verify that if you take this function u and plug it in here, this solves Laplace's equation. And if you take this function v and plug it in here, it also solves Laplace's equation. Really easy to verify. You can try this for f of z equals z cubed, or z to the 4th, or z to the 5th. You'll get this kind of Pascal triangle pattern of x and y's, and those functions are going to be solutions of Laplace's equation. Same thing with the real and the imaginary part of the exponential function, the cosine function, the sine function, and so on and so forth, any analytic function. And so that's really, really cool, is that there is a deep, deep connection between the solution of one of the most important partial differential equations ever written down, Laplace's equation, and these very special complex functions called analytic functions. Good. Okay, so I think what I want to do now is, that's kind of the main thrust of this lecture. So now what I'm going to do for the rest of the time is I'm going to derive what these Cauchy-Riemann conditions would look like in polar coordinates, because that's kind of cool. And then I'm going to give you a couple of important theorems that are true for complex functions that we're going to use later when we do things like contour integrals. So I think the next few lectures are going to be, so we talked about derivatives in the complex plane. the next few lectures, we're going to talk about integrals in the complex plane. When we start doing, path integrals and contour integrals, these are kind of the complex baby version of things like Gauss's theorem and Stokes's theorem. So Green's theorem is derived in the complex plane, and we're going to see what happens when we integrate analytic functions and non-analytic functions. Good. So what do I want to show you right now? So I'm going to write down Cauchy-Riemann in polar coordinates. So let's say Cauchy-Riemann. I wish I knew how to spell. I think this has two M's. Please forgive me. Cauchy and Riemann. Cauchy-Riemann conditions in polar coordinates. Good. And so essentially what we're going to be doing is we're going to be saying, and this is super weird, we're going to take, f of z equals u. It still has a real part, but we're going to write u as a function of r and theta, plus iv, which is a function of r and theta, where z equals r e to the I theta is written in polar coordinates. So it's kind of weird because I'm still writing my function f in kind of Cartesian real plus I imaginary, but I'm writing the argument z in polar coordinates. You could do the other way. You could say f of z equals u e to the iv, and you could have that be a function of r and theta or of x and y. So there's actually multiple ways of kind of you can write z in polar and f in Cartesian. You can write z in polar and f in polar. You can write z in Cartesian and f in polar. And you can derive kind of 4 different versions of the Cauchy-Riemann conditions if you are a masochist. OK, good. So Cauchy-Riemann in polar is going to be something to the effect of partial u, partial r. The squeakiness, actually, I find very reassuring. It means I've been writing, equals 1 over r partial v partial theta. That's one of the Cauchy-Riemann conditions. And partial v partial r equals minus 1 over r partial u partial theta. And again, if you were going to be solving Laplace's equation in polar coordinates, if you were dealing with the steady state heat distribution, so this would be good. These rectangular coordinates would be good to find solutions of Laplace's equation for things like the steady state heat distribution or the electrostatic distribution, on a rectangle in a rectangular coordinate system. But if I wanted to find the steady state heat distribution for a circular plate of metal that I'm heating at the boundaries, then I would be wanting to use the polar form of the Cauchy-Riemann conditions, which are, again, going to give me solutions of Laplace's equation, but in polar coordinates, which is kind of neat. And there's always simplifying notation. If we define u sub r equals partial u partial r, and if we define u sub theta equals partial u partial theta, and so on and so forth, so subscript here is partial derivative, then this expression here, in that notation becomes kind of nice and simple. It becomes, let's write it out, u sub r equals minus 1 over r v sub theta, and v sub r equals minus 1 over r u sub theta. And I'm only writing it these 2 ways because you're going to see mathematicians use whatever shorthand they particularly like, or physicists or engineers. And sometimes people use subscripts for partial derivatives. So I just want you to kind of see these are the exact same thing, just written with different notation. Good. OK. So those are the Cauchy-Riemann conditions in polar coordinates. You can derive, I think what you really should do is you should actually compute the derivative of this, as r goes to 0, and do you can kind of derive these. That'll require a little bit of thought of how you can relate the Cartesian Cauchy-Riemann conditions to these polar Cauchy-Riemann conditions, but you certainly can derive these. I think what I'm going to do now is I'm going to actually show you that log of z is analytic away from the origin using these polar Cauchy-Riemann conditions. And then I'm going to give you those integral theorems that I talked about earlier. So I'm probably going to fast forward as I erase all of this nonsense. It's actually not nonsense, it's super important. OK, so what I'm going to do now, this is kind of a piece of this lecture, is I'm going to verify that log of z is in fact analytic away from z equals 0. Away from z equals 0. Remember, the log of z is a weird function. It's infinitely valued, and I'm just going to write it down. So like log of z equals, and I'm going to write it down in exactly this form. Okay, so that's why I'm deriving Cauchy-Riemann in terms of the real plus imaginary part of f, but in polar coordinates for z. So the log of z equals the real valued logarithm of r plus I times theta principal. And we know that there's a plus 2 pi, k, where k is an integer, that is also valid here. But remember, this is again a legalistic kind of technical math detail, and sometimes it's important to be legalistic with things. Analytic functions have to be single valued. So when I talk about the log of z being analytic away from the origin, what I technically mean is, this log function, if I look at x and y and I look at the v component, this log function is like a spiral staircase, an infinite spiral staircase, where every time I go around, I get, I can add 2 pi, 2 pi, 4 pi, 6 pi, 8 pi in the phase, or I can subtract 2 pi, 4 pi, so going up or going down. We are specifically talking about only the principal angle, the principal logarithm, where theta is in 0 to 2 pi. Okay, so that's kind of the first level of this infinite spiral staircase. I don't know if any of you like Stephen King or The Dark Tower, but whenever I think of I think The Dark Tower is basically a complex logarithm. Maybe he took a complex analysis class in college, and we're only on the first level. That's where humans live, in this principal branch of the complex logarithm. Good. So we're talking about this principal branch of the complex logarithm, and I'm going to get rid of the p, and I'm just going to call this theta to make my life a lot simpler. We're on the principal branch of the complex logarithm. Theta is between 0 and 2 pi. And so as long as I talk about that branch, this log function is analytic away from z equals 0. And we're going to verify that using these Cauchy-Riemann conditions. So again, that's why I wrote it in this weird kind of way, where this is u of r theta, and this is v of r theta. And it's kind of nice because, u is only a function of r and v is only a function of theta. So you're going to see that kind of trivially this is actually true. And we'll just do that. So kind of clearly we have that u sub theta, because u is only a function of r, partial u partial theta equals 0. And because v is only a function of theta, partial v partial r is also equal to 0. That's certainly true. And u sub r, if I take the partial of this with respect to r, it's just 1 over r. And v sub theta equals 1. Okay? So let's just kind of verify these two Cauchy-Riemann conditions. So Cauchy-Riemann 1 is that partial u partial r, I don't know why I use capital R here and lowercase r here. I'm sorry, that's super confusing. These r's are all the same. They should all be capital R's. Big R, big R, big R. I don't know what's wrong with me. Big R, big R, big R. Those are all big R's. Sorry, this is a mess. But you get what I'm saying. Those are radii. Cauchy-Riemann 1, partial u partial r is 1 over r from here, and that equals 1 over r times partial v partial theta, which is 1. Yes, in fact, 1 over r equals 1 over r, away from r equals 0. Good. And then Cauchy-Riemann 2, this one, partial v partial r equals, definitely partial v partial r equals minus 1 over r partial u partial theta. 0 equals 0, also true. 1 over r v theta. This is also true because those are both 0. Both of these are true as long away from r equals 0. Because I have this 1 over r, something weird happens when r equals 0. But these Cauchy-Riemann conditions are absolutely satisfied, and these are exactly equal to each other, and there's no weirdness as long as r is greater than 0, as long as I'm away from that origin. If I'm at the origin, I would probably have to do something like L'Hopital and verify that in fact these are not valid. These do not hold. That function, that derivative, ddz of log of z equals 1 over z, blows up to infinity at z equals 0. So it does not exist at z equals 0. But log of z has a derivative where it is independent of the direction of that derivative for all z away from the origin, at least on its principal branch. So log of z is in fact analytic on its principal branch away from the origin. Very important point. We're going to use that later when we do complex contour integrals. And if I was thinking about this, I would want you to actually really show from these conditions that you can derive these conditions, and vice versa. I would write something like, r squared equals x squared plus y squared, and theta equals maybe like, r cos theta equals x and r sine theta equals y, and I would try to compute partial derivatives and show that these equalities are the equivalent and necessary and sufficient for these equalities to be true. That would be like a really nice exercise if you're actually taking this class in my math class. That probably is going to be one of the exercises I ask you. And it's probably a good 30-minute or 60-minute exercise. If you're pretty fresh on your calculus. If you're a little rusty, it probably would take me about 2 hours right now to really nail that down. Okay, so that's why I'm not doing it right here on this whiteboard. Good, so what have we done? We've shown that the Cauchy-Riemann conditions are solutions of Laplace's equation. These functions u and v are the solutions of Laplace's equation if they satisfy Cauchy-Riemann. We have derived Cauchy-Riemann in polar coordinates. We didn't derive it. I have written it down, and I have asked you to derive it. Big difference. And we have shown that if you believe that this is true, then that we can use that to show that the complex logarithm is in fact analytic away from the origin and on its principal branch where it's single valued. Okay, so I basically take the spiral staircase and I cut out the first level of that spiral staircase, and I only analyze that. If I was being, again, a legalistic mathematician, I'd give this a name like, fancy log on level 1, something like that. I'd just make up some notation that we're only talking about that first level of Stephen King's Dark Tower. But very important, this is going to be super useful, this property that complex log is analytic everywhere away from 0. Specifically, what that's going to allow us to do is in the complex plane, if I'm giving you the punchline for a couple of lectures in the future, if I have a closed contour C1 and I have another closed contour C2, what I claim is that the integral of C1 of log, my fancy pants log on the first level, log of z, dz, because log is analytic here. Analytic. Log is analytic in this domain. Log is not analytic everywhere inside of this curve, but it is analytic here, so this integral is going to equal 0. And what I claim is that on this second contour, the integral on this second contour that has this weird singularity point of log z dz, that's going to equal 2 pi I, okay? Because if I go around in a circle around that origin, I climbed and I added 2 pi I to my phase angle. So I'm going to pick up a 2 pi I here. This is essentially Cauchy's integral formula. Very, very important when you do things like try to compute inverse Laplace transforms and things like that. You can solve some pretty hairy integrals using this kind of weird idea of integrating around singularities. But if I integrate my logarithm anywhere else that doesn't contain this point, everything is well behaved and fine. So I'm going to have like a whole lecture dedicated to this. I just wanted to give you the punchline and kind of anticipate what we're going to see later, why we care about things like analytic functions and points where things are not analytic and things like that. Good. Okay. So there's probably one or two more things I want to show you. These are properties of analytic functions and how we are going to use them in the future based on the fact that they have Taylor series. So I'm going to state these properties now, and then I'm going to use these properties in future lectures, okay? And I feel like complex analysis is really quite interesting. It's a very fascinating field. Like if you like calculus, you're probably going to like complex analysis. And my students are usually kind of polarized. Some of them, they're very polarized. So some of them love complex analysis. Some of them hate complex analysis. I'm a little bit more ambivalent because I think it's super duper interesting. And 50 years ago, it was the primary way that we thought about solutions of partial differential equations. Before computers, when we were stuck with pencil and paper, complex functions was one of our gateways to opening up partial differential equations. And it still kind of is. We still benefit from that intuition, even though now we can solve these things with computers. So again, I'm a little torn. I don't teach a 15-week, full semester class on complex, but I do have this intense 2-week boot camp because there's deep intuitive things that you need to know. That said, these things are kind of confusing, right? It's hard to picture. We can picture things in 3 dimensions, but complex variables, a complex function that has a real part and an imaginary part over a variable that has a real part and an imaginary part, that's like a 4-dimensional space. We don't really picture it, and it's pretty confusing. So I'm going to encourage you to really, take your time and review these concepts. You might need to play these back or do some examples on pencil and paper and really think about these things. Good, okay. I'm going to erase this, and then we're going to jump forward to the thing I want to tell you. Okay, so last thing I want to tell you are these not integral theorems, just general theorems. And again, you could, if you don't like theorems, if you just want to see how to use these things, maybe this is a little technical and legalistic, but I'm going to do it anyway. Theorem 1. And I've said this a bunch of times in the last lecture, so you might not have known that this is something that needs to be proven. It's a theorem, it needs a proof. I'm not going to prove it. A function f of z, which has a real and an imaginary part, u plus vi. Sometimes I write iv, sometimes I write vi. Okay, so this function is going to be single valued and have partial derivatives and satisfy Cauchy-Riemann condition. And it is analytic if and only if it satisfies Cauchy-Riemann. So a function f of z that is single valued, and has continuous partials, partial u, partial x, partial u, partial y, partial v, partial x, partial v, partial y. So if my function is single valued and it has continuous partial derivatives that do in fact exist, that you can write down, in a domain, remember we're talking about regions of the complex plane, in a domain D, which may or may not be all of the complex plane, but it's inside the complex plane. That's what this means. It's a subset or equal to the complex plane. The function is analytic in D if and only if, very important, it is analytic if the thing I'm going to say is true, and it is only analytic if the thing I'm about to say is true. In math, we write this IFF. That means if and only if. It's a necessary and sufficiency condition, if you like math speak. If and only if the Cauchy-Riemann conditions, the Cauchy-Riemann, have I been spelling it right the whole time? The Cauchy-Riemann conditions are satisfied at every point z in the domain, are satisfied at every point z inside this domain. Good, okay, so I've said this a million times up until now, right? We know that for our function to be analytic, for us to be able to do calculus on it, for Analytic is the key property that we are checking for this function f of z. F of z is analytic if and only if the Cauchy-Riemann conditions hold. That's what I'm trying to say. Our function f of z, it needs to be single valued. That's just a definitional thing. It has to be single valued. And if its partial derivatives of its real and imaginary parts exist and are finite and satisfy Cauchy-Riemann conditions, then that is necessary for it to be analytic, and that's sufficient for it to be analytic. If this is true, then f is analytic. If f is analytic, then this is true. That's what that's saying. And if you were in a proper 15-week complex analysis course, you would be proving that this is true. There would be like more under the hood, and there's certainly kind of deeper math there. I want you to be able to use these things. I want you to be able to use functions that are analytic. I want you to be able to tell when a function is analytic, check the Cauchy-Riemann. I want you to know what you can get out of a function that's analytic, like you can compute its derivatives and you can do contour integrals around it. And I want you to know what happens that's weird when a function is not analytic, like if you integrate around the log function around a closed orbit that contains a non-analytic point, a singularity, or kind of a degenerate point that the function is non-analytic. So that's kind of, I don't really care about exactly proving that this is or isn't true. Take my word for it, or take Cauchy and Riemann's word for it. But I want you to know how to use this theorem and property, because we're engineers. Okay, there is some really beautiful mathematics, but I want you to be able to use these things. The other theorem, let's call this theorem 2, and this is Goursat's theorem. I always thought that was kind of a cool name, Goursat theorem. Goursat's, that's not how you write theorem, but that's the Goursat's theorem. If f, this is a weird one. This is a super, super, super interesting one. If f of z is analytic at z, which means these are true, then f of z has continuous derivatives. This is going to be weird. Wait for it. It has continuous derivatives of all orders. Like not just the first derivative of z, but the second derivative of z and the 19th derivative of z. If you like Stephen King, we're all about the 19th derivative. All of the derivatives. That's bonkers. Why is that true? All I required here is that first partial derivatives are equal or exist and satisfy Cauchy-Riemann. If that's true, if my function is analytic, then this tells me that in a neighborhood around that point where z is analytic, in this domain D, all derivatives of f of z have to exist. F double prime exists, f triple prime, f, the 19th derivative, the 577th derivative, all exist in that domain. So that's really interesting. It essentially means that I have continuous derivatives of all higher orders if my function is analytic. That's unexpected, but very, very important. And kind of the main implication of this, is that f of z is analytic if and only if, right, or double f, if and only if, and this is at some point z naught, some base point z that I'm considering, if and only if its Taylor series converges to the function in that neighborhood, let's say exists, and converges to f of z in a neighborhood, got to be in the neighborhood of z naught. So essentially I have some z naught, I have some neighborhood of z naught where I have some z. And what this means is that if my function f is analytic at this base point z naught, all of the derivatives are continuous and exist, and the function has a convergent Taylor series in some neighborhood of that base point, which is really cool. It means that if I know z not, and all of the derivatives at this point, I can specify my function value at anywhere else in this domain that the function is analytic. This is the basis of something called analytic continuation, and it's really, really interesting. It basically means, if I have a domain D that's really big, my function is analytic on this massive, massive, massive domain, and I have a ton of information over here at z naught. I can compute z naught and its derivative, its second, third, fourth, fifth, and so on derivative. It means that I can actually extend and define what that function value is everywhere in this domain. I can tell what my function value is here just from properties over here because it's analytic. And of course, that isn't so surprising to us in real valued functions. That's kind of how we think of Taylor series in the first place. But here, it basically means that we can do that. We can extend kind of our neighborhood of definition of this function until we hit a non-analytic point. Like maybe there's a cliff here where now it's non-analytic and I can't use those derivatives after this cliff. I lose information after that cliff. Or maybe there's a cusp here, and that's where I lose the ability to extend my function beyond that point. Okay, good. Two very important theorems. And again, we're going to think about how we can use these to solve integral equations and contour integrals and things like that in the next lectures. Okay, thank you.